In this video, I want to define velocity and speed. Let's start by noting that velocity is a magnitude and a direction, and speed is just a magnitude. So it's similar to the relationship between displacement and distance. So based on this, we can recognize that velocity is a vector and speed is a scalar. To further define these variables, let's consider a race car going around a 1-mile oval track. So here's the car in location A. At this location, let's say the car has a speed of 180 miles per hour and a velocity going to the right. So we'll put this coordinate scheme on here and we'll call the right the positive x direction. And then an eighth of a minute later, the car is in position B. And let's say the car at position B has a speed of 100 miles per hour or a velocity of 100 miles per hour in the positive y direction. So it's probably obvious to you then that the instantaneous speed is the magnitude of the instantaneous velocity. For practical reasons, it's often easier to calculate the average speed and velocity rather than the instantaneous values. So here's the equation for the average speed, where d is the distance traveled and delta t is the elapsed time. And we can calculate delta t by t final minus t initial, which we should now know based on our previous discussion of what delta means. Also, note the bar I put over the s for speed. The bar means average. So when you see me use that, I'm identifying the variable as an average. And here's the equation for the average velocity. Notice that the average speed equation is what most people are familiar with, distance divided by time. And then the average velocity equation is displacement divided by time. So that's the key difference between those two. Just a quick mathematical comment. Anytime an equation is delta something over delta something, like this equation, then the result is an average. So in this case, we know that we're calculating an average velocity because it's delta x over delta t. Okay, back to velocity and speed. A key point I want to make at this stage is that the average speed does not always equal the magnitude of the average velocity. Let me demonstrate this by using the race car example. As a reminder, the instantaneous velocity at position A was 180 miles per hour in the positive x direction, and the instantaneous velocity at B was 100 miles per hour in the positive y direction. And these numbers are the instantaneous speeds, so it's just the magnitudes of the velocities. So now let's calculate the average values between positions A and B. Note, by the way, that an average is always between two instances in time, or these two locations A and B, as opposed to the instantaneous values, which are at location A or B, or at any particular location, or at an instant in time. Okay, anyway, so we want to calculate the average velocity and speed between A and B. Let's start with the average speed. Here's the equation, where d is, of course, the distance traveled. The distance traveled in our picture is here. So since this is a 1/4 mile track, a 1 mile track, then let's say the car has gone 1/4 of a mile. And then the elapsed time, we're told, is 1/8 of a minute, or 0.125 minutes. So we can plug those values into the equation, and we get that the average speed is 2 miles per minute. So now let's calculate the average velocity. Here's the equation, where delta x is the distance between the initial and final positions. So that is a straight line distance shown here between positions A and B. Clearly this is less than the red path, the 1/4 of a mile path we had before. So let's say it's something less. Let's say it's 0.23 instead of 0.25 miles. Okay, and then the time is the same. The time is 0.125 minutes. So we plug these numbers in, and we find that the magnitude of the average velocity is 1.84 miles per minute. And that's compared to the average speed we just calculated of 2 miles per minute. So unlike instantaneous values, the average velocity and average speed are not always the same. And the reason for this is that the distance traveled here is not always the same as the displacement here. So let me summarize a few key facts. First, with the instantaneous values, so they apply to just an instant in time, and the instantaneous speed is always equal to the magnitude of the instantaneous velocity. But then for average values, so they're the average between two instances in time, and the average speed does not always equal the magnitude of the average velocity. So the last thing I want to mention in this video is something I call a trip problem, which is basically a trip or a race that can be broken up into multiple segments. It's basically an application of the speed equation. So as an example, you might have a problem like this. A person drives a car for an hour for 60 miles, at 60 miles per hour, then stops for 15 minutes and then drives for 90 minutes at 50 miles per hour. What's the average speed for the entire trip? So you would look at this and recognize that there are three time segments. There's one where the driver is going at 60 miles per hour for an hour, then stops for 15 minutes, then drives for at 50 miles per hour for 90 minutes. I'm not going to work this particular problem out. I've worked out another trip problem. I think actually I called it a speed problem when I posted the example, but it's the same thing. So look on Moodle. Look at the trip problem that I posted. I outlined the procedure to handle this kind of a problem, and then come back and do this problem that I'm showing you here. And here's the answer, 49.09 miles per hour, and see if you get the same answer by following the procedure. And that's it for this video.